Good afternoon and greetings to all. On behalf of Sardar Vallabhbhai Patel University of Agriculture and Technology, I welcome you all to the fifth day of our Faculty Development Program on Applications of Mathematical Techniques in Agriculture, Science and Technology. Today, we are privileged to have two distinguished academicians with us, Dr. Jitendra Singh Man from MIT Hamirpur and Dr. Sanjay Kumar from GB Pant University. We sincerely thank both our resource persons for graciously accepting our invitations. With gratitude, I now invite our first resource person for the day, Dr. Jitendra Singh Man. Sir, have you joined?
Yes, am I audible? Am I audible?
Yes, sir, you are audible.
Okay. So,
hello.
Hope my screen is visible.
Sir, will you be sharing your screen with us?
Yes. Is it visible?
No, sir, your screen is not. It's coming in, sir.
Okay. Is it visible now?
Not yet. Not yet, sir. It's loading. Sir, can you make it slideshare mode? Slideshow?
Yes, it is in slideshow mode. I think maybe internet issues. I have already shared full screen.
All right, sir. It is visible to us now.
Okay. So, good afternoon, everyone. Thank you so
Kindly
much.
allow the opportunity.
Thank you so
Sorry
much.
to interrupt you, sir, but can you please allow me?
Yes, yes.
Sir, please allow me a moment to introduce you to our participants.
Sure.
Dr. Jitendra Singh Man, Assistant Professor Mathematics, Department of Mathematics and Scientific Computing, NIT Hamirpur, Himachal Pradesh. Dr. Man has completed his PhD in mathematics from IIT Dhanbad, Jharkhand. With more than 5 years of teaching and research experience, he has contributed significantly to academia by publishing over 20 research articles. Today, the topic of his talk is modern developments in harmonic analysis using index Whittaker wavelets. Welcome, sir. You can continue.
Okay, thank you so much, madam, for your kind invitation. And I am thankful to all of the organizing team. So the title of my talk is Modern Harmonic Analysis using Index Whittaker Wavelet. So here the two terms is harmonic analysis, and I have used one term that modern development and using Index Whittaker Wavelet. So outline of this today's presentation is basically, I have used index Whittaker wavelet transform to develop a new tool in wavelet theory, that is continuous wavelet transform with respect to index Whittaker. And later on, I have described the discrete version of this continuous index Whittaker wavelet transform. So what is wavelets actually are? So wavelet is a wave-like oscillation with an amplitude that begins at 0, increases and decreases back to 0. The concept of ondulets or wavelets started to appear around 1980s. So this concept can be synthesized as a thought of various ideas originating from different disciplines of mathematics, physics, and engineering. So the idea of wavelet was first introduced by a geophysical engineer, Jean Morlet, around 1982 for providing a mathematical tool for seismic wave analysis. So the idea of wavelet came into existence to achieve a good time resolution for high frequency transient and good frequency resolution for the low frequency components. So it is well known that wavelet plays an important role in various fields of science and engineering like image processing, biomedical engineering, signal processing, and computer vision. So basically today's my talk is from the functional analytic point of view. I will discuss the various mathematical properties of wavelet, obviously index Whittaker wavelet. So what was the drawback? How the theory came into picture? First, notice that means wavelet means understanding the idea of signals. The very first transform that came into picture before the wavelet transform was Fourier transform. The actually, if you look at the Fourier transform, the output of Fourier transform is in the frequency domain, right? So it is not possible to analyze a signal at what time it changes in frequency domain. So to overcome such drawbacks, so the picture of wavelet transform came into existence. Now, how to define a wavelet transform? So wavelets are a family of functions that are constructed using translation and dilation of a single function, which is a member of L2. If you look at this, this is the mother wavelet. Here the translation is x minus b and dilation is defined in case of usual Fourier, that is 1 over modulus of c multiplied by 1 over c, where c and d both are real numbers and c is not equal to 0. So that this should right hand side should have a usual meaning, where C defines a scaling parameter which measures the degree of compression or scale, and D is the translation parameter. Now, the same equation can be represented in terms of integration by this structure. Now, if you look at this function, this is actually a dilation which is defined in this pattern, and this function dzxd, it is defined in terms of Dirac delta function. If you remember the definition of Dirac delta function, you simply will get this right hand side. So these two are same notation if you represent this family of wavelet in terms of integral, right? So in the same way, if you scale position very smoothly, then the transform is defined as the continuous wavelet transform for any signal f, which is a member of L2. And with respect to wavelet phi, you will define a continuous wavelet transform. And if you look at the right hand side of this equation, you will see that wavelet is a special kind of convolution operator, and the associated wavelet is called classical wavelet. Now, uh, since this translation and dilation will differ for the various integral transform, so various wavelet came into picture by for in case of various integral transform. For example, many authors define wavelet in terms of fractional Fourier transform and studied their properties. So in addition, few more wavelets are defined in the literature, which are defined on positive half line, which are Bessel wavelet transform, Laguerre wavelet transform, Kontrowitz-Lebedev wavelet transform, and discuss their application. Now, what is the need for defining the index-Whittaker wavelet transform? The index-Whittaker wavelet transform is a powerful tool for the treatment of integral transform with index-Whittaker convolution type. So their convolution and generating operators plays a fundamental role for the study of this index-Whittaker transform. So motivated by the previous study, so this task is to, this work is to define the wavelet using the basic properties of index-Whittaker wavelet transform. So first of all, our entire study will lie in the space of LP of all those real valued measurable functions which are defined on the positive half line, such that the norm is defined by this for p ranging between 1 to infinity, and for the p equal to infinity, it is defined in the terms of supremum of this function. And here, if you look at the definition in our space, here a measure is involved. Later on, while defining this index-Whittaker transform, I will let you know what is the role of this measure. And this, just because of this measure, this transform has some special properties that we will look into it. So therefore, this space is obviously a Banach space. Now, an index integral transform with Whittaker function as the kernel has been studied by various authors. For example, Srivastava, Al-Musallam, Sousa, and Baker has extended his study to mathematical physics. So my task is to define wavelet transform associated with the index-Whittaker transform. So first of all, I will let you know what is integral transform. This is, if you look at this integral transform, this is the kernel of this transformation. This is the function. Here is the function measure is involved. So what is integral transform? It is a method of function transform in which a function is mapped from one function space to another via integration, and kernel plays an important role. So the kernel of this transformation is this Tricomi function multiplied by our signal, which is under study, and this is the measure of this transformation. So this is in our literature, and in present work, I will use this definition of index-Whittaker transform. And if you look at the kernel of any integral transform, that is actually some special function, which is a solution of certain differential equation. Obviously, if you study Laplace, Fourier, or any other transformation, for example, Hankel, Kontrowitz-Lebedev, Miller-Fock transform, all these are special functions which are solution of differential equations of order 2. Now, here the function which serves as the kernel of our transformation is actually represented in terms of this Whittaker function, which is a solution of certain differential equation of order 2. And further, if you want to expand this using some well-known confluent hypergeometric function of the first kind, So you can rewrite this Tricomi function as this. And further, if you want to expand this Tricomi function in terms of integral representation, so our kernel will admit the following integral representation, one in the Legendre polynomial form and other in terms of gamma function. So one more important thing is that we have the estimate of our kernel, means our kernel is controlled by this Tricomi function and which has the following asymptotic behavior. So what is the role of studying this? So various property in the upcoming section, which we will deal through the functional analytic point of view, will use this result, right? And for the systematical study of any other transformation or any integral transformation, one should know its inversion. So for the positive A, the inversion of the given transformation. Now in this space L2, where the measure is referred to be as rho A tau, is given by this equation number 3. And nothing to confuse with this measure. Just to cancel out the measure in the original definition, which was involved as MAX. So the inverse will have this rho A tau. Now one can find the adjoint of the equation number 1, that is IW transformation. Just keep the measure outside and keep the rest of the entries as it is inside the integral, and its inversion is given by the equation number 4. Now to study any transformation, one should note its convolution structure. So the confluent hypergeometric function of second kind with different arguments in the kernel. If you look, x and y are the different arguments of the kernel, and their product is equivalent to the integral representation, which is given by 5. If you look, this is actually the kernel, this is our function, and this is the measure with respect to IW transformation, right? So I can rewrite this as actually IW transformation of this function qxyz, and this qxyz actually a function which is symmetric in 3 variables x, y, and z, and it is here the function. If you look at D, this is a parabolic cylinder function which is solution of certain differential equation. So by the definition of index Whittaker transform, you can write this as IW transform of this function q, and I can conclude to this step. And to obtain the integral representation of q, so apply the inverse transformation to this right hand side, and you will get this in terms of 3 different arguments of the kernel in terms of x, y, and z, and our inverse transformation with respect to measure rho A tau. So this is the simple calculation how to obtain the integral representation of this q. And this is one of the important property that this function q has the integral value equal to 1, right? And to study for the translation operator of a Whittaker transform, we have this equation number 9, which is represented by this, and its adjoint is given by this. Just keep the measure outside and rewrite all the equation inside the integral. This is the simple technique. And one should note the convolution. In case of Fourier, how one can define convolution? Integral over any set, that is R, f of x minus y, g of y, dy. But in case of this Whittaker, we will apply the translation structure. Since our translation is an integral operator, so this single integral will turn into double integral. So the convolution structure in the sense of Whittaker convolution is given by equation number 10. So here are the some important results that I will use in the upcoming section to obtain few properties of this index Whittaker wavelet. That is, if you apply IW transformation over the translation function, you will get the kernel times the IW transform of the function. And this is the important result. It is mainly true for Laplace. It is true for Fourier until and unless there is a factor of how you define Fourier 1 upon 2 pi, and Hankel transform, Kontrowitz-Lebedev transform. If you apply IW transformation of convolution of two functions, you will get the product of the corresponding IW transform of the functions. So, and this is one of the basic results. If f is a member of L2 and g is a member of L1, then this norm convolution in L2 space is controlled by the product of these corresponding norms in the spaces L2 and L1 respectively. So proof is obtained in this, and this is an obvious proof. So we have the Plancherel and Parseval relation for our index Whittaker transform and its corresponding adjoint operator. So if you consider this equation number 14, if you take f equal to g, you will get this Parseval relation. And similarly for the adjoint, we have equation number 16. And when f and g behave alike, this will reduces to this equality, right? Now our all results are developed for the index Whittaker transform. Now with the help of all those results, our task is to define the continuous index Whittaker wavelet transform. So for any function f which is a member of L2 is called a Whittaker wavelet if it satisfies the admissibility condition. So this is the admissibility condition. Whenever I say that phi is a wavelet or anything is a wavelet, Whittaker wavelet, that should be a member of L2 and this integral should converge or it should be finite. And we will define our dilation by this following fashion. That is, you simply multiplied the function and scale the function, right, with positive value of c. Now, since wavelet is defined in two different ways, the first is translation. We will change the central position of the wavelet along the time axis, and the second one is scaling, that is dilation. So basically, this wavelet can be defined in terms of translation and dilation. So here comes the definition. So this is the wavelet which is a member of L2 that is defined using help of translation and dilation. Remember, our time translation is an integral operator. So integral of this function multiplied by this q and this measure, right? And dilation is simply defined to scale pi of Caesar. So this integral will be our Whittaker wavelet. Now, with the help of this wavelet, we will define our continuous wavelet transform for a continuous signal. So it is represented in terms of this, and it is actually a special sort of inner product. And we remember that we have already obtained its integral representation in equation number 18. So this continuous Whittaker wavelet transform can be expressed in terms of this double integral, that is equation number 20. Now here comes the very first theorem, that is the existence of continuous Whittaker wavelet transform. So for any function f which is a member of LP space and phi in LQ with p and q restricted between 1 and infinity, and this continuous Whittaker wavelet transform. Then we have for the arbitrarily fixed value of c, this our continuous Whittaker wavelet transform is continuous with respect to variable b on this domain. And again, we have this norm of this continuous Whittaker wavelet transform in this space is controlled by the product of these two norms, where P, Q, and R related by this conjugate relation. And this relation number C is directly a consequence of B if you take R equal to infinity. That is, if you take R equal to infinity, this will be L infinity, and rest of the norm will remain as it is. Here it changes to 1 since 1 over infinity is 0. Now our interest is to check the continuity of this IW transformation. So take any arbitrarily but fixed point in this domain and apply Holder inequality. So consider these two difference of the argument of continuous wavelet Whittaker wavelet transformation and apply Holder's inequality, right? Since you know that this integral of this q x y z in the beginning I have told that is controlled by 1. So this modulus of this entire bracket is controlled by 2. So taking b tending to b naught, delimiting behavior, that will give the limit 0, and hence it will prove the continuity of this continuous Whittaker wavelet transform. And rest of the proofs are obvious and can be seen in this literature. Now here comes some important properties of this continuous Whittaker wavelet transform. Suppose you have two wavelets phi 1 and phi 2, and alpha beta being a complex number, and FG we are two signals in L2, then we have the following property, that is linearity of this IW transform continuous Whittaker wavelet transformation and anti-linearity property, right? So here comes the important result that I will basically used while defining the Parseval and reconstruction formula. So if phi is a member of L2, then the index Whittaker wavelet transform of one of this wavelet is given by this. If you apply IW transformation, you will get the kernel times this IW transformation of the wavelet, but this has some usual meaning which is represented by this integral. Now this is simple. Just remember the IW transformation definition. Just remember that this is our family of Whittaker wavelets. You know the definition this in terms of this integral, and I am applying the IW transformation. So kernel times the function that has been already expanded in terms of integral with measure max. Now you can apply Fubini theorem, that is change of integration is possible. Just keep it outside. And this is actually, if you look, IW transformation of this function. And clearly, you remember that this can be expressed in terms of the product of two different arguments of the kernel. So I am replacing this function, this inner bracket, by the product of the kernel with two different arguments in terms of b and xi. And what does this mean? This is constant since the integration with respect to xi, and what remains inside is nothing but the IW transformation of this function. So this is actually nothing but psi f phi of c tau is actually the product of c into tau. From this you can conclude, right? From this point. So here comes the lemma that if phi f is a member of L2, be any function, and phi is a wavelet which is a member of this, then we have the following relation holds true, which is given by equation number 22 and 23. Both are same. If you prove one of the things, the rest will follow automatically. So just remember the definition of continuous Whittaker wavelet transformation. You remember this, and but if you know by the previous result, so this is actually kernel times the IW transformation of this quantity. Yes, and this is nothing but, if you look, that this is a function and this is a function and this is the kernel, right? If you apply the Parseval's relation, you will appear, this is the actually measure with respect to inversion. This is the kernel and these are the two functions. So this is simply the inverse IW transformation of this function with this function, and thus our result holds true. Now I have in the beginning told that this wavelet transform, continuous wavelet transform more precisely, is a special kind of convolution operator. So what in the case of index Whittaker transform? Yes, it is also a continuous, it is also a convolution operator. I can show it. So this is actually our continuous Whittaker wavelet transformation. So if you remember that this is actually nothing but translation of this function. So this can be represented in terms of translation and rest of the entries as it is. And if you see that this is nothing but the translation and this the rest of the function. So this is actually a convolution. So hence our continuous Whittaker wavelet transform is also a convolution operator. Now let us take one example. Now consider function f of the form x to the power beta, where a is controlled by beta and both are positive, non-negative set. Then we have, by the definition of continuous index Whittaker wavelet transform, just replace this fx by x to the power beta, and by the well-known integral by this lemma, I can represent it in terms of product of two Tricomi function. So this is the value of this integral. Now to convolute this with the wavelet, now I am choosing B-spline mother wavelet of order 1, which is represented by 1 if zeta belongs to this strip and otherwise 0. So for value of phi of c I will be 1 when zeta will be between 0 to 1 over c and 0 otherwise. So this integral will reduces to 0 to 1 over c, since the domain of integration is this 0 to 1 over c is 1 and rest of the entry is 0. So this will reduces to 0 to 1 over c and this value as it is. So this is what we obtain the continuous Whittaker wavelet transform, right, of the given function. Now what is the reconstruction formula? So is it possible from a given family of wavelet, are you able to restore the original function f? Yes, it is possible. So let f is a member of L2. Now sigma of c being a weight function, such that this special admissibility condition equation number 26 is satisfied. And we are considering another family of wavelet generated by translation and dilation of the considered wavelet. That is actually a transformation of considered wavelet. Then f can be restored in terms of this double integral. So by using relation 23 and 1, if you remember that this is actually given by relation number 23 in terms of product of these two functions. Now to prove, we have to prove this. So multiply by sigma of c and this weight function in terms of variable c. So we have the following integral reduces to this. So how I can write this as constant, because remember the definition in the assumption 26, I have took the value of this c5 to be this integral and this is finite. So I can replace the right hand side of this while integration with these terms by multiplying, and this comes out to be this, and transferring this term to the right hand side, our function will be represented by this. Now applying Fubini, if you look at this is an isomorphism between two spaces. So if you see that this IW transformation of this function, this is actually the kernel and this is the function, and this is look at the IW transformation of this function. So our fx can be restored by the inside double integral. So hence it is verified. Now next is the characterization of this another family of wavelet. So now assume that there exists a positive constant A and B such that A and B are related by this relation 28, and we have another wavelet pi c which is defined using the previous wavelets 29. Then we have the following relation holds true. So this is actually the definition of this wavelet. Now, if you look at this is the product of the kernel with two different arguments. You can replace this by the function QA in terms of the single integral in the beginning of convolution structure. While defining, I have told that this can be expressed in terms of this integral. So I have replaced this term by this integral, which is basically for obtaining the value of QAXYZ, here change of variable in terms of B. So if you look by the definition, this is actually a translation of this function. And from 27, you have, and by 28 relation, you have this following inequality that simply take the measure on both sides, integrating both sides with respect to rho at tau to this, you will obtain the next result. Now, to prove that if phi is a member of L2 is a Whittaker wavelet, then translation of this function is again a Whittaker wavelet. Now, I have already told you that to show that any function is a wavelet, that should be a member of L2 and it should satisfy the admissibility condition. So by the well-known reference, if phi is a member of L2, then its translation is a member of L2. Now the one thing is done, that it is a member of L2. Now rest is to prove the admissibility condition. So this result by equation number 11, you know that if you apply W transformation over the translation of this any function, you will get the kernel times the IW transform of that function. Now consider the admissibility condition for this function. Now, by this, we know that by the asymptotic nature of this kernel, this is controlled and is finite in the domain of integration. So we can take it outside. And what remains inside is this. And since we know that this is a wavelet, it should satisfy the admissibility condition. If this is finite, this integral is finite, this is finite. So the entire thing is finite, and hence it satisfies the admissibility condition. So it can be clear that if phi is a wavelet, then its translation will also be a wavelet. Now, next thing is that, yes, if phi is a Whittaker wavelet and h is a bounded integrable function in L1, then its convolution is a wavelet. Yes, it is a wavelet. Now, since phi is a wavelet, it means that it is a member of L2 and its norm L2 is finite. And h is bounded integrable function in L1 and its norm is also finite. Now, rest of the thing is done by the, in the beginning, I have told you the lemma that if f is a member of L2 and g is a member of L2, then their convolution is a member of L2. So this convolution will become a member of L2. Now, rest of the thing is that I have to obtain the admissibility condition. And you remember, if you apply IW transformation of the convolution of two functions, you will get the product of IW transform of two functions. And this is a bounded integrable function. So this is finite in the range of integration. So basic property, this is finite and rest of this function is a wavelet and its integral is finite, and hence the entire quantity is finite. And this clearly shows that the admissibility condition is satisfied and the convolution is a Whittaker wavelet. Now, here comes the important result, that is the Plancherel relation in case of Whittaker wavelet. So we have phi1 and phi2 to be a member of L2 be a Whittaker wavelet, such that this function psi a phi1 of c tau is defined by this, right? I have already told you that this is actually nothing but the same this function in the beginning we have obtained the lemma, right? And I'm strict with this weight function sigma of c to be c e to the power a e to the power c with the weight function, so that this will no longer depends on tau, and this satisfy our admissibility condition. And then we have the following integral turns out to be equivalent to this condition. So we will prove this. Let f and g be a member of L2, and then consider this integral. Now by relation, I forgot the relation. Yes, by equation number 22, you can see that this term can be represented as inversion of this, and similarly, you can apply inversion of this, right? Both are the same thing. You take the conjugate and you apply the inverse of this IW transformation, right? So you will have this bracket. Now further, by the adjoint of this IW transformation means isometry isomorphism, you can rewrite this step, and by simply cancelling out, it will turns out to be this integral. And again, integrating this previous integral there means we have to show that this double integral is equivalent to this. So integrating, we will get this, and this is nothing but our admissibility condition. That is, this is actually IW transformation of F and its conjugate. Now this is in the space of this. By the Plancherel relation of IW transformation, you can change this term to be integration 0 to infinity fx g bar of x max dx, and this is the required result. Now here are some consequences. If you take phi1 equal to phi2, then you have this following notation of the double integral. If you take f equal to g, you will have this, and both are equivalent, then you have this more solid form of the given Plancherel relation. Now next is the composition of continuous Whittaker wavelet transformation. So composition of Whittaker wavelet transformation or wavelet transformation is defined by using the theory of Fourier transformation, which was discussed by Pathak. And motivated by the work of Pathak, Prasad et al. Extended this theory to the fractional Fourier transformation. So in this section, I will discuss the composition of continuous Whittaker wavelet transform and some of its properties. Now let us define and make a clear definition for the composition in case of Whittaker wavelet. Suppose I have two wavelets, phi1 and phi2, and F is a member of L2, and this is actually our continuous Whittaker wavelet transform with respect to variable PQRS on this domain R plus. Then the composition is defined by equation number 32. And once it is defined, then this can be rewritten by using previous outcomes as equation number 33. So the admissibility condition. So let us assume that because whenever you will define a wavelet, you must require an admissibility condition. So in this case, let us assume that the function phi1 and phi2 are the Whittaker wavelets, such that this is already I have told you, but I am strict with our weight function that zeta1 of q will be referred as this and zeta2 of s will be referred as this, just because of this measure involved in the definition to cancel out some terms, so that this C phi1 and phi2 will no longer depend on tau. So this is referred as the admissibility condition in case of composition of continuous Whittaker wavelet, which is 34. Similarly, as we define the Plancherel relation for the continuous Whittaker wavelet transform, we will define the same way for the composition of Whittaker wavelet transform. Now let's take phi1 and phi2, which is a member of L2 be a Whittaker wavelet, which define composition. And later, if you look at this to be the composition with respect to argument f and g, which is a member of L2, and zeta1 and zeta2 as defined above, then we have this triple integral is equivalent to this value. So this phi1 and phi2 is admissibility condition as defined in this previous slide. Now let us consider this integral same as we have discussed the proof just in the previous slide. We will follow the Plancherel relation in terms of adjoint. So we have this integral, and using Parseval relation, we will arrive to this step. So, and the same consequences will follow for the proof of this theorem, right? If f equal to g, then we have this result, right? Now, next is discrete wavelet transform. So what is the need for defining a discrete version of any wavelet? why continuous version is not enough to deal with. So there are mathematical structure, or there may be some thing involved in the problem. We have the representation of signal in we need to take the representation of signal in discrete version. So it is applicable in signal processing, image processing, and biomedical engineering. So in signal processing, data are represented by finite number of values. So discrete version of the continuous Fourier transform found to be useful in these cases. So more precisely, it can be achieved by choosing the discrete value of translation and dilation parameter. The very first thing is, just like the admissibility condition, here we will deal with some stability condition in case of discrete wavelet. So for any function phi which is a member of L2 is called a dyadic wavelet if it is satisfy the following condition, where Z runs over the set of integers and A and B are positive constants such that both are finite and non-negative. Now, here I will first define semi-discrete wavelet transform, then I will come to discrete wavelet transform. The name itself tells us that semi means you have to translate only one parameter into discrete one. So I am discretizing this dilation parameter C, which is represented in terms of 2 to the power minus j, and B belongs to R plus. This remains a continuous variable, but this is discrete, means dilation is discrete. So again, remember that this continuous wavelet transform, which was defined earlier, that can be represented in terms of inner product, but here our parameter dilation turns into a discrete one. So I am replacing C by 2 to the power minus j. The same calculation will work. And again, I can show you that in case of semi-discrete wavelet transform, this is again a convolution structure, right? So using the Parseval identity as established for the continuous Whittaker wavelet transform, we will arrive to this stability condition, which is represented by 39. So the same thing what we have did for the continuous wavelet transform, we will do it for the semi-discrete wavelet transform and later for the discrete wavelet transform. Now let us assume that the semi-discrete wavelet transform for any function f which is a member of L2 as defined by this 38 by this relation. And let us consider another wavelet var which is defined by 37 by means of Whittaker wavelet, and it is of the form equation number 40. Then our f can be restored by this value, right? This value. So if you remember, in case of continuous Whittaker wavelet transform, there was double integration. Since here we have discretized the dilation parameter, so that one integral will turns into summation. So this was the basic difference in the calculation. So in view of this previous definition, now let us consider the left-hand side of the right-hand side of this integral. There is nothing much tough calculation involved in this. So summation, this is actually, if you expand the definition of this, so we have the inverse of this transformation. So we have this rho a tau. I am expanding the definition of this inverse IW transformation of this function. So this will be the kernel. This will be the kernel. The function remain as it is, right? And measure will be rho a tau, and rest of the entries means expand the definition of this semi-discrete wavelet transform. Here it is, right? And if you remember that this can be represented in terms of this convolution by this, right? So this can be rewritten in terms of this convolution, and you remember that IW transformation of product of two function is simply IW transformation of these two functions. Now this is the function, this is its conjugate, and remember that this will be by equation number 40. This will turns out to be the value of this. Now this will get cancelled out, and what remains is this integration 0 to infinity. This is nothing but the IW transformation of this function. That is, this will cancel out, and this simply remains the function fx only. So under this theorem gives us the motivation that the reconstruction of this function f is possible under circumstances which ultimately leads to the definition of dyadic dual of a dyadic wavelet. So what is the definition? A function f var phi, which is a member of L2, is called dyadic dual of a dyadic wavelet phi if for every function f which is a member of L2 can be expressed in terms of this value, and using previous outcome, the stability condition for this dyadic dual of a wavelet will reduces to this, right? Now, next thing is that here is one remark that the dual of wavelet is not always unique. If you can remember, refer to this reference 7, there may exist dual which may satisfy the stability condition. If a dyadic wavelet phi satisfies the stability condition, then phi is a basic wavelet satisfying this, and if A equal to B, then this result will reduces to this. This is very simple. Just consider the equation number 37, that is the stability condition. Just yeah, just divide by tau and keep on integrating between 1 to 2. So we have this step 41. Now this can be rewritten, this term can be rewritten as, this can be rewritten as, just put the substitution 2 to the power minus j tau as eta. So this integration will changes to 2 to the power minus j, 2 to the power minus j plus 1, and this will be eta, and denominator will be eta. So d eta. This, remember, this is actually the admissibility condition. If you just apply this summation over this integration, this will turns to 0 to infinity. Just keep on expanding j. This will be 0 and this will be infinity, and hence this we conclude that we have this admissibility condition in this case, right? If A equal to B, you have the another result. Now, till now we have, in the semi-discrete part, we have discretized only the dilation parameter. Now we will discretize the translation parameter as well. Now our task is to discretize this B to obtain the discrete wavelet transform from the semi-discrete. So this, I am using this representation, since I am discretizing this B, that in terms of Bjk, k over 2 to the power j B naught. So for some B naught, this B naught is referred as the sampling rate or sampling positive constant. So thus the discrete wavelet transform will be represented by this semi-discrete, can be represented in terms of discrete by this following quantity. C is 2 to the power minus j, we already know, and this bjk is nothing but a notation, that is k over 2 to the power j. The same thing what we have did for the semi-discrete part will do for this discrete portion also. This, now we have discretized this parameter, so we have to, that again will be a convolution structure, just there will be a slight change in this. So here is the change. So this will be V naught Jk. Just remember that this will be k into 2 to the power minus j B naught, same thing. So it is again a convolution. Now, hence the stability condition works well for the discrete wavelet transform, which is represented by 44. Now, same thing as we have obtained the reconstruction formula for the F. So in case of semi-discrete wavelet transform, so same thing we will do in case of discrete wavelet transform for any function f which is a member of L2 satisfying the defined by 38 and satisfying the stability condition 44, and let T be a bounded operator defined on this Hilbert space, then Tf will be represented in terms of this discrete wavelet. Then F can be restored from above data by this in terms of summation, and where this discrete wavelet is represented in terms of this. So from this well-known reference, one can conclude that T is a one-to-one bonded operator onto this space and T inverse exists. Let us define G in terms of TF. This inner product is equivalent to this. And if you remember that A times T inverse norm G is nothing but, since T inverse G is F, so same thing is F. And if from this you can conclude that this can be controlled by the inner this can be controlled by this quantity, and this is actually nothing but TF with inner product of these two functions. And if you take the definition of G as TF, this will be G and this will be T inverse G, right? And by applying Schwarz inequality, we will arrive to this result, and hence F can be restored from its discrete version by this result, and where this has some usual meaning, that is, this quantity is represented by this. Now, lastly is the important property related to frame and rise basis. This is actually a property of discrete wavelet transform. The theory of frames and bases have been developed recently in recent years, which came into picture as a mathematical tool in signal and image processing. So in this self-contained work, frame and raised basis are presented from a functional analytic point of view, emphasizing their mathematical property. A raised basis is an image of orthogonal basis under an invertible continuous linear mapping. So perturbing a raised basis by a small amount yield another raised basis. Frames have many property of basis but lack important one, that is uniqueness. So here is some literature related to this. We will not go deep into it due to restriction of time. So we will see some property of this discrete wavelet and study raised basis in L2. So here comes the definition of tight frame. A frame, a function f, which is a member of L2, is said to generate a frame using this discrete wavelet of L2 with sampling rate T naught. If equation 44 holds for some a and b, if a equal to b, that is referred as tight frame. So this was the equation number 4. That is nothing but the stability condition. All right. Now, here the function of raised basis, the function f, which is a member of L2, is set to generate a raised basis for this discrete wavelet with sampling rate b naught in the following assertion. If the linear span of this discrete wavelet is dense in L2, or there exists a positive constant a and b such that this stability condition is satisfied, where the coefficient djk comes from this square summable space of square summable sequences, and here a and b are referred as the bounds of this discrete wavelet, that is the raised bound. So now here is some important theorem. If phi is a member of L2, then the following statements are equivalent, that the discrete wavelet is a raised basis in L2, and this discrete wavelet is a frame of L2, and also L2, this space is linearly independent in the sense that this summation is equal to 0. That is, this linear sum is equal to 0, and this linear sum is 0. Means this is Li, means these coefficients all are 0, and these coefficients are coming from this space only. Moreover, the raised bounds agree. So the proof of this scheme of this proof is similar to the proof which was proposed by Chui in case of Fourier. So we will apply in case of our discrete Whittaker wavelet transform. So using relation 46, that is the definition of discrete. It follows that the raised basis is a member of L2, and this discrete wavelet be a raised basis with raised bound given by A and B. Now consider the matrix operator P, which is given by this discrete wavelet. If you look at this matrix capture relationship between wavelet. It is actually a positive definite matrix with all eigenvalues as positive. It is a nice matrix, means our wavelets are non-redundant and can represent any signal. So its entries are given in terms of the inner product of these two. Now this function, this zeta lmjk, this tells us how much wavelet lm overlaps with the wavelet jk, right? So the b naught is the sampling rate or initial sampling constant. So we are dealing with these two wavelets, discrete wavelets, and by the stability condition we arrive to this result. And I have already told that this matrix is a positive definite matrix. Then we denote its inversion by this, and by some well-known result, these values are actually nothing but some product of Dirac delta function of these two wavelets Lj and Nk, right? And again, by applying the discrete stability condition, this permits us to allow the another wavelet. This is actually a dual basis, means a partner set of bases with the original wavelet to allow the reconstruction of this f. And from some 47 and 48 relation, that is this outcome, one can clearly say that this is a basis of L2 which is dual to this discrete wavelet, and hence we can reconstruct our f in terms of this discrete wavelet, and for which the stability condition is given by 50, and this proves that 1 implies 2. And similarly, as we have proved for the discrete version, the previous result theorem, the converse is true for this by using the Brans-Steinhaus and open mapping theorem. This follows that our discrete wavelet is a raised basis in L2. So these are the references which I have used. So these are the important reference if you want to study application of wavelet in biomedical engineering, which is given by reference 1. This related to Whittaker function in sense of mathematical physics. This is also an introduction to wavelet, that is important book to study basic things related to wavelet, and time frequency analysis by Dovesius. So these are all about the references I have used. So thank you so much.
Thank you so much, sir, for your insightful session. We are now open for a brief question and answer session. If anybody has any question, they can unmute themselves and ask, or they can also drop it in the comment box. We'll read it out for you. If anyone from the participants has any kind of question or will like to bring us something up, they can unmute themselves and ask the question directly to the resource person. Alternatively, you can also leave it in the comment box. Sir, as I do not see any questions coming in, I would like to take this opportunity to propose the vote of thanks. Dr. Mann?
Okay.
Yes, sir. On behalf of the organizing committee, I deem it a great privilege and honor to extend a vote of thanks for his insights on modern development and harmonic analysis using index Whittaker wavelets. The clarity of your presentation, the depth of your analysis, and the way you simplified a complex topic have surely benefited our participants. Your talk has truly added immense value to our today's session and subsequently to our FDP program as well. We look forward to more such valuable sessions from you, sir, in the future. Thank you once again.
Thank you so much and best wishes.
Thank you. Dear participants, we'll wait 5 more minutes for our second resource. The feedback link has been posted in the chat. You can access it from the chat section of the Zoom or from the WhatsApp group. Dear participants, kindly do not leave the session. Our resource person will be joining us in a minute or two. Dr. Sanjay Kumar, are you here with us? Have you joined, sir? Dr. Sanjay Kumar, have you joined us? Sir, your screen is visible to us, but somehow we cannot hear you. Sir, your device is muted. Can you please unmute yourself? Sir, we are unable to catch your audio.
बाहर से बोल के आता
Okay.
हूँ।
Sir, your video is visible. Your screen is shared with us, but we cannot hear you. Your audio is not compatible with the system.
सही
I see you are trying to speak, but we are unable to catch your audio, sir. Dear participants, we are trying to resolve the issue at the earliest. Kindly coordinate.
हेलो हेलो अब तुम लोग वहां से बोलो जरा देखो मैं ऑडिबल हूँ क्या
हाँ सर
Yes, sir. Yes, sir.
ओके
We can hear you.
ओके
Yes.
तो
Welcome, sir.
so I don't need to wear this device,
Sir,
okay
can you please allow me a moment? I would like to introduce you to our participants.
okay
Moving forward now, we are honored to have our second resource person for the day, Dr. Sanjay Kumar, Professor Mathematics, Department of Mathematics, Statistics and Computer Science, GB Pant University of Agriculture, Pantnagar, Uttarakhand. Dr. Kumar has completed his PhD in mathematics from GB Pant University of Agriculture, Science and Technology, Pantnagar, with more than 20 years of teaching and research experience. He has published over 80 research articles and has made remarkable contributions in the field of applied mathematics. Topic of today's discussion would be fuzzy logic and its application in agriculture sciences. Over to you, sir.
hello
Yes, sir.
yeah am I audible I think so
Yes, sir, you are audible and your video is also on and we can see your screen that you
okay
have shared with us.
good afternoon to all the participants and thank you the organizing committee of this faculty development program for giving me a chance to share my little knowledge about this fuzzy set theory and its possible application in the field of agriculture sciences. As I'm aware that this faculty development program is on the application of mathematics in agriculture. Okay, so there is no point to discuss. Many applications of mathematics are found in the agriculture, especially if we talk about the differential equations, if we talk about the uh, linear programming problems, or if we take about this, differential calculus and integral calculus, all they have the versatile applications in the field of agriculture sciences. And in fact, the many part of the agricultures or basically the natural sciences or biological system automatically follows the rule of mathematics. Okay, I'm sure that many of you know about the Fibonacci sequences and many of the things surrounding to us follow the pattern of this Fibonacci sequences. For examples, we have the many flowers plants in which the number of petals are some member of the Fibonacci sequences. Branching of the trees follow the pattern of this Fibonacci sequences. Okay, in fact, nowadays for the stability and for the optimizations, we are also taking the help of these Fibonacci sequences for developing the irrigation efficient crop systems and greenhouse design. Okay, but I'm not to suppose to talk on these applications of mathematics in field of agriculture, and I hope that in past few days few lectures have already been organized on this topic, like what branches of mathematics are applied in the which branch of agriculture sciences. here I am to talk about that, how we can take the help from this hardcore mathematics to this soft computing kind of the things, or we can talk about that, in what way this fuzzy set theory is applicable in the field of agriculture sciences. Okay, so this lecture is going to be some very basic kind of the things, like you will be familiar that what is the foundations of fuzzy logic, what are the fuzzy sets, how they differ from the classical sets. Okay, what is the rule base, how the inferencing is done in this fuzzy inference system. Okay, this is the part which has to be covered, or which needs to be covered before talking about the applications of fuzzy sets in agriculture. Okay, so as you all know, as I told you, this is the most important part of this mathematics which is used in the field of agriculture, that is the differential equations. Okay, and we all know that differential equation is the mathematical equation that relates a unknown function to its derivative and represents how a quantity change over the time, or with respect to some other variables. Basically, in every cases, in almost every cases, our focus is to find out the relationship between the input variable and output variable. In context of computer science, or in context of this, other branches, we say the input variable, output variable. In context of mathematics, we call them as the dependent variable and independent variable. Okay, so basically, differential equation is nothing but it is a function, it is relates a function or unknown variable, that is a dependent variable, to the derivative of the dependent variable with respect to the undependent variable. And the key applications are found in the crop growth and biomass productions, nutrient cycling, okay, and in many other branches of this agriculture. I hope if any of the lectures in past lectures, someone has covered that, the famous mathematical models which are based on the differential equations, and they are very popular in the field of agriculture sciences. Some of them are this Richards equation, Lotka-Volterra equations, crop growth models, and epidemiological models. Okay, I'm not supposed to discuss all these things in this one, because my focus will be there on this applications of fuzzy logic and fuzzy set theory in the field of this agriculture system. Another branch of this mathematics which are very much applicable in the field of agriculture sciences, you are very much aware, that is the linear programming kind of the things. Okay, in linear programming problem, we always distribute the resources, or we always interested to utilize the resources in such a way that we get the maximum number of the profit, maximum profit. For example, like if you look at this a simple problem, here a farmer has 70 acres of land available for the planting 2 crops of soybeans and wheat. And this table is basically denoting that, what is the cost of the preparation per acre for soybean and wheat, how much days are required per acre for the soybeans field and wheat field, and what is the expected profit per acre from the crop of soybean and wheat. And the problem for the farmer is that, he cannot spend more than 800 rupees in the preparation of the field for both soybean and wheat field. And he is also limited to total of 120 working days. And then we have to decide that, or he has to decide that, how many acres of each crop should be planted to maximize the profit. It is a very simple linear programming problem in 2 variables. Okay, and you know how this can be solved. Problems, you will assume that X and Y are the acres which will be used for this soybean field and wheat field. Okay, and then you will construct the objective function that will be 180x plus 100y. This has to be maximized with respect to the constant 60x plus 30y is less than or equal to 1800. 3x plus 4y is less than 120, and that can be solved by the graphical solutions. Simple problem. Okay, you can also have the many constraints, some more variables there, or the linear programming problems of 3 variables, that all can be done. And these are very much used in the field of agriculture. But you have observed one thing, whatever mathematical model you apply in your lab or in your room, if the things goes according to that model in the field, you don't get that kind of the result. Some variations is there, some deflections is there sometimes, and you say, no, this model is not working fine, I'm not getting the desired result as it is supposed to produce. Problem is, these mathematical models are basically based on the very hard kind of the assumption. These mathematical models are not tolerant to the uncertainty, which is because of the many reasons. Okay, I hope that you have heard this word. Nowadays, this is very popular in our surroundings. That's hello.
Yes, sir. Continue, please, sir.
Yeah. Okay, so this is a very basic problem of this linear programming. But I was saying, like, the mathematical models, they are based on the very hard kind of the assumption and do not provide the desired result, or the results or variation in the result is found when they are applied in this field or some outside of the lab. And that is because of that, they are not capable for handling the uncertainty. They are not capable of handling the uncertainty, probabilistic uncertainty, and the uncertainty because of the reason other than the probabilistic reasons. You are aware that, the statistics is used to use the probabilistic uncertainty that happens because of the randomness. But there are many reasons which also cause of the uncertainty, and one of them is this, the imprecise information, vague information, linguistic representation of the data. Okay, for time being, suppose if you are giving the information using some linguistic variable, not using some crisp value, it is going to cause a uncertainty. And that kind of the uncertainty is not handled by these all mathematical models and is not handled by the statistical tools. Okay, so to handle the uncertainty that arise in the system, not because of the randomness, because of some other reason, this fuzzy set theory was incepted. Okay, and here this slide will explain you that why we use the fuzzy logic. These are the few reasons, and when you start to use this fuzzy logic, you will find that there are the number of the reasons which promote the applications of the fuzzy logic. First of thing, fuzzy logic is conceptually easy to understand because it is based on the natural language processing. Fuzzy logic is flexible, it is not hard. Okay, and it is the tolerant of uncertainty that occurs in the system because of the reason other than randomness. This fuzzy logic can be blended very much with the conventional control techniques, and fuzzy logic is based on the natural language and is very much capable to handle the data represented in the linguistic form. This fifth reason, this is a very important, which makes the fuzzy logic very popular. Because in our normal life, every times we don't play with the numbers. We don't play with the numbers every time. Sometimes, if everybody asks you that, how cold this is, then you will not exactly tell him or her the temperature. You will give the information, no, it is very cold or it is very hot. It is not very cold. It is not very hot. That kind of the things like, so in our daily life or in our routine life, every time it is not possible to provide the input in form of the crisp numbers or numerical values. Sometimes we wish to provide the input in form of the linguistic information. And all these mathematical and statistical models are not capable for handling the linguistic representation of the information. That's why they fail when they are used to take the uncertainty because of this reason. Okay, so how do you find this fuzzy set different from the classical set or crisp set? You are aware, you must be aware about the classical set or set because it is nowadays taught in the class of 10th or 9th, even in 8th standard also it is very much known. And in classical set, what happens if you are making the collection of some object, then you should not have any hesitation or any that kind of the condition which make a particular element member or not member of that collection. Means किसी particular element को किसी collection के अंदर डालने के लिए आपके पास कोई हिच नहीं होनी चाहिए कि whether I should put that element in this collection or not. And that will be done if you are making the well-defined collections of the object. This word is very important. Like, there should not be any kind of the uncertainty whether this element will be the member of that collection or not. And that will be done only when you have characterized those elements by some particular conditions. That's why we always say that the well-defined collections of the object is called a set. And so if you look at set of integers, set of real numbers, set of rational numbers, there is no doubt. Okay, integers will always remain integers if they follow the full conditions or full property of the integers. Full property of the real numbers, that will be the member of the real numbers. Okay, then set of rational numbers. Contrast to, so there are only two possibilities, like, if we define the classical set in terms of membership functions, it will have only two values, either 1 or 0. Membership value of that element in that collection will be 1 if it is the perfectly member, and it is 0 when it is not belonging to that collection. In contrast to this one, okay, for example, if I take a set of tall people, okay, and I have decided that the person having the age either 5 feet 10 inches or more than this will be considered as tall. Okay, so all the persons having the height 5 feet 10 inches and more than this will be the member of the collection of tall element, and the person having the age height of 5 feet 9.9 inches will not be the member of that collection of the tall set. It is not going to happen in the case of the fuzzy sets. This kind of the crisp boundary is not found in the fuzzy sets. That is the beauty of this fuzzy set. Okay, so in natural language, the class or the collection does not follow the well-defined property of the crisp set. For example, the collection of tall students. Here, this tall is the weak term. Collection of the real number very near to 10. Very near to 10. Okay, so 9 will also the member of this collection. 9.5 will also the member of this collection, but of course with the different level of the belongingness. So in these cases, the boundaries of these collections appears to be vague. That is, it is not defined. It is not defined. Okay. So what are the fuzzy sets? Fuzzy sets are the extension of classical set. In classical sets, the membership of element in a set are assessed in a binary terms according to the crisp conditions. In classical set, a fuzzy set implies a set without the crisp boundary. Okay, so so this is the graphical representation of the membership functions of the set of tall people. Here you will see everyone. This the person is having the age of 5 feet 2 inches is also belongs to this set of tall people. 6 feet 10 inches also belonging to this one. Everyone here except from here to here, they are all having the 0 membership grade in this fuzzy sets. Rest of other are having some grade. So here the membership function, and every fuzzy set is characterized by its membership function, and it is a curve that define how each point in the input space is mapped to the membership value between 0 and 1. Okay, so in contrast, in classical set theory, the membership was either 0 or 1 only, but in fuzzy sets, you will find the membership grade between 0 and 1. 0 if it is not belonging to that set, 1 if it is exactly belonging to the set, and between 0 and 1 if it is partially belonging to the set. Okay, so the fuzzy set gives us the liberty to consider the partial belongingness of an element in the collection. This is the mathematical representation. Okay, this is the mathematical representation of the fuzzy set real number near to 0. Okay, this is like, you know, the representation both in terms of the crisp set, in terms of the fuzzy set. In crisp sets, the person having the age of 180 centimeter or more than this will be considered tall, and rest of other will be or not considered tall. Here, everyone will be considered tall with the different level of the belongingness. Different type of the membership functions are found, and the most popular are the triangular, trapezoidal, Gaussian, well type, G well type membership functions. These are some mathematical equations, and these can be find out very easily. Like, this is nothing but it is simply the straight line joining the 2 points that you can easily find out the graph of this triangular function, trapezoidal function, Gaussian function. These are the standard function which depends upon the mean and variance. Okay, G-well, sigmoidal membership functions, G-well functions. They are all very much popular and they are used in the fuzzy inference system. Okay, this is important concept, like, for developing the fuzzy inference system for the agriculture system, that what are the basic operations supported by the fuzzy sets. Okay, and these are very much same, like, or you can say these are the generalization of the union and intersection and complement of classical set. Okay, both complement, suppose if capital A and B both are the fuzzy sets, then A bar, it is the complement, A union B, this is the union of those two fuzzy sets, and A intersection B is A, and this is the intersection of the fuzzy sets. All three will be again the fuzzy sets. And their membership function, because every fuzzy set is characterized by its membership function. So A bar, this will be characterized by this membership function, and this is nothing but 1 minus mu AX. Okay, so if suppose some element in fuzzy sets A has a membership grade 0.8, then the same element will have the membership grade in its complement, in the complement of fuzzy set A, as 1 minus 0.8, that is 0.2. Okay, and A union B will again of fuzzy sets, and its membership function will be denoted as this one, and this will be defined at the maximum of membership grade of X in fuzzy sets A and membership grade of X in fuzzy set B. Okay, here A intersection B will again a fuzzy set, and its membership function will be the minimum of X, minimum of the membership grade of X in the fuzzy sets A and membership grade of X in the fuzzy set B, whichever is the minimum, that will be the membership grade of X in A intersection B. Okay, and this is the graphical representation of complement, intersection, and union. And here capital A and capital B, these are the two fuzzy sets whose graphical representation is this one. Okay, so if you look at, this is the maximum, and here if you see, if you plot, try to take the maximum area covered by these two functions, this will be this one. So this is what, this is the graphical representation of A union B, and the minimum one is this one. So this portion denotes the graphical representation of the intersection of the fuzzy sets A and B. Okay, as you know, the A union B, this is, if you take the complement, so here this is 0, now it will become 1. Here this point A is 0, here it will go to this one. So if you look at the reverse of this one, that will be the membership function for the complement of A intersection A union B. Now, why this is important, because our objective is to develop the fuzzy inference system for agriculture system, and these fuzzy inference systems are basically the rule-based system, and those rule-based, the antecedent parts are connected by AND operator or OR operator. Okay, so as you know, AND denotes the intersection, and OR denotes the union. Okay, so we should have these expressions, especially these two, have the very important role in developing the fuzzy inference system. Okay, so this is basically the block diagram of the fuzzy inference system. You have some input data. Okay, that input data is in form of the crisp values or numerical values. Okay, then you have to fuzzify them. Okay, that will be fuzzifier means you are fuzzifying the input. Okay, then you will develop some rule base. Okay, then those rule base will be inferenced, the output will be computed, that output will again in form of the linguistic form, so that has to be defuzzified in the numerical form. So from numerical input to you have the numerical output, but before that one, that numerical information or crisp information to be converted into the form of the fuzzy cells. This is basically the things like, this is the crisp input, crisp, this is the crisp, it has been made fuzzy, and these are the rule base. If X is A1, then Y is B1. A1 is your input fuzzy sets, Y1 is your output fuzzy sets. Multiple rules are there. Okay, all those rules are aggregated. Then you will have some common surface. You will find out the center of gravity methods, center of that output surface. And further you defuzzify to have the numerical output. This is the uh, simplest block diagram of any fuzzy inference system. Only changes here will be here, like, you will have the multiple input, single output, or multiple input and multiple output. Here, only single input is considered to make it simple. Okay, these are the some basic methods which are used for the finding for the defuzzification purpose means to convert the linguistic output in terms of the numerical output. These are the some mathematical terms. Okay, so basically what where is the problem? Like, problem is there, like, if you have number of input variables and you have a single output variable, and the relationship between them is linear, okay, then you are lucky enough. In most of the cases, or in every real life applications of this control or everything, whatever you take, the problem is that, the relationship between the output variable and input variables, this is non-linear. So what a fuzzy inference system implements, it implements a non-linear mapping from its input space to output space. We are not interested that, how they are related to each other, but here we are simply mapping the input space to output space using this non-linear mapping. Now, this part, as I told you, this inferencing, this inferencing, this is basically, if number of rules are used to find out the output, then how they are combined. That is basically the inferencing. Okay, so this is the most commonly used max-min composition method for the reasoning scheme. And I just explained, what is going to happen. Suppose you have the two input X and Y and one output Z. Okay, and this is the value of X, and in this fuzzy sets A, this is the membership grade. This is the Y, and this is the membership grade of Y in fuzzy sets B1. And rule is, if X is A1 and Y is B1, then Z is C1. I will find out the firing strength of this rule. If X is A1 and Y is B1, then Z is C1. I'm using this AND operator. AND denotes the intersection, and in intersection we take the minimum of two membership grade as I told you in the previous slide. So what I will do, I will take the minimum of these two, and this output fuzzy sets will be clipped by this scale. Suppose for the same input, this second rule is fired. Again, the same thing is done. This is nothing but this value, minimum of these two will be called the firing strength of the rule. The firing strength of this rule 1, it clips this consequent part of this rule. Firing strength of this rule clipped the consequent part of this fuzzy rule. Then using this shaded region, a combined surface is obtained and the center of gravity is computed of this combined output to have the crisp output corresponding to the input small x and small y. This is basically the reasoning scheme of this one. Okay, for example, this is the simplest example. If x is small, then y is small. If x is medium, y is medium. If x is large, then y is large. Input is from -1 to 1, and y is output is from 0 to this one. Okay, so this is these are the fuzzy sets for the x and y, and this is the outputs for generated. This is the example where I'm taking the two input x and y and then one output, that is your z. Both all x, y, and z are belonging to this interval. These fuzzy sets are constructed for x, y, and z. Okay, then this output surface is generated, and then using the max min composition, the centroid defuzzification use, and then the output is computed. Okay, now there are basically two types of the fuzzy inference system. One is called the Mamdani fuzzy inference system, and another is the Sujano fuzzy models. Okay, so before discussing this Sujano, I will talk about this. This was the case of your Mamdani, and here you will find, like, in rule base, this is small, and this negative large. All these are the fuzzy sets. So here, the main difference between the Mamdani fuzzy inference system and Sujano inference system is what? Antecedent part of the fuzzy rules are fuzzy set, but the consequent part in the Mamdani fuzzy inference system is fuzzy sets, while in Sujano, this is the mathematical function. In Mamdani, it was also the fuzzy sets, but here in the Sujano, it is the some polynomial between x and y. Okay, this is basically the main difference between the fuzzy this Mamdani inference system and Sujano fuzzy inference system. For example, here you will find the rule base something like this. Okay, so now as you can see, the output is given in form of the numerical value. So no defuzzification is required when you are using the Sujano inference system, and it is done simply like that. These will be your again the inferencing will be this one. Suppose this is output from the first rule. This is the output from the second rule. Firing strength of this one is suppose say W1, which is again the minimum of the membership grade of this one and this one. Firing strength of this rule is W2, which is again the minimum of this value and this value. And then the output will be nothing but the weighted average. Okay, so in this way, we compute the output in this Sujano inference system. This is something like this. And this slide I have included, like, here in place of fuzzy set, I have taken the crisp rule. Okay, so here the output surface is not smooth. While if I take the fuzzy sets instead of crisp sets, here I will get the smooth surface. Okay, so this is the way to use this Sujano inference system. Okay, so this is, I don't think that I have the time to discuss this thing, but you should have some idea of this. The very first extension of this internistic fuzzy sets in terms of the internistic fuzzy set. This is basically, you know, what happens in the case of the fuzzy sets if an element is having the membership grade in some fuzzy set, say 0.7, then automatically we consider that the non-membership grade of the same element in that fuzzy set is 0.3. You got it or not? Means if I'm taking an element, say small x, its membership grade in the fuzzy set, say capital A is 0.7, then its non-membership grade is automatically comes out as the complemented value from 1. Okay, but you know, very often this doesn't happen. This is something like that. If you take the survey of 20 people or 50 people and say whether this faculty development program is good. Okay, if 40% people say yes, it is good, it is worth, then in fuzzy sets automatically we will assume that the 60% people say no, it is not worth. It happens in the case of the fuzzy sets. While in case of the internistic fuzzy sets, we say if 40% person are saying that the course is good enough, okay, there may be some kind of the percentage which are not in the position to decide whether it is good or not. Okay, so there is some kind of the non-determinacy. Okay, so automatically we will not consider the non-membership grade of an element as the complemented value from 1. What we will do, we will use the two separate function. One will decide the membership grade of that element in that set. Other will decide the non-membership grade of that element in that set. Okay, and that will become an example of the internistic fuzzy sets. And it happens when there you feel some kind of the non-determinacy there. Okay, so this was the notion of internistic fuzzy sets, okay, in which we are using the two separate function for using the membership function and non-membership function, and it is done, or it is introduced by this Atnasov in 1986. Nowadays, we also talk about the internistic fuzzy inference system. Some more extensions have also come up, like in form of the hesitant fuzzy sets, Pythagorean fuzzy sets, picture fuzzy sets, but you know, here we do not have the time to discuss all those ones. So we will focus especially on this, you know, the applications of fuzzy inference system in this agriculture. Okay, these are the some basic operations which we can take. These are nothing but the generalization of those ones. Now, here is the question that why we should use the fuzzy sets in agriculture. As I told you in the starting, that fuzzy sets are capable for handling the uncertainty that happens in the system because of the imprecision, because of the vagueness, because of some other factors which are not controlled by the random variable or random process. Okay, it happens, and agriculture system or agriculture sciences, in agriculture sciences, the maximum time of the uncertainty because of these things. The probabilistic uncertainty, up to some extent, you handle by using the statistical theory, by doing some replications, by doing some repetition of the experiment. Okay, but very often the things happens in the field which cannot be controlled by the statistical process. Okay, so these things means the lot of uncertainty in the agriculture system because of the non-randomness makes it is very suitable for the application of the fuzzy sets. Where you will find the applications of fuzzy sets in agriculture? No need to say like, agriculture engineering is using this fuzzy set theory and fuzzy inference system and the equipment designed using the fuzzy logic very much. Okay, in precise farming, in Internet of Things and other things, we are using this fuzzy set theory based equipments for the agriculture system. But beside that also, we can also use this fuzzy set theory for the classification of the soil and the evaluation of the fertility of the soil. We can develop the fuzzy inference system for the irrigation scheduling. I have included one example of this. You can also develop the fuzzy inference system, both Mamdani and Sojano, for the prediction of the crop yield system. And you can also develop the fuzzy inference system for the post disease management, precision farming. And this is the very important things where the versatile applications of the fuzzy set theories are being in decision support system. As you know, the agriculture system or agriculture sciences, it is depending upon the number of criteria. That criteria may be interdependent, that criteria may be dependent. And every time the criteria information provided to the user is not exact, is not precise, is not in the crisp form. It is provided in form of linguistic, it is imprecise, it is having some vagueness. Okay, so you will find the number of applications of fuzzy set theory in multi-criteria decision-making problems, especially designed for the agriculture sciences. Okay, around 10 years back, we started and we use this Mamdani fuzzy inference system, okay, just to predict the economic yield of 6 different variety of the rice. Okay, this was the initiative by some department, our department, not our department, by the Department of Plant Physiology. Okay, so this was the here in this paper we developed the Mamdani fuzzy rule based system, okay, in which some 2 inputs were taken and the output was in form of this economic yield. Okay, just as I told you, like, this I have included an example just to illustrate the thing that, how you can design or you can develop the fuzzy inference system for the irrigation scheduling. Okay, this is the information. I told you input will be given in form of numerical value. So here I have taken the 2 input. One is soil moisture and another is temperature. Range of soil moisture is in this interval from 0 to 100, and temperature is in the range from 10 to 45. I told you these numerical values has to be fuzzified. Fuzzified means using these, you will define some fuzzy sets in this range for soil moisture, in this range for temperature. I have taken the 3 membership function, and those membership functions are of trapezoidal form. Okay, these are the parameters. You all know how to define the trapezoids. Okay, so one is medium, one is dry, one fuzzy set is dry, another is medium, and another is wet. These three linguistic variables are used for soil moisture. Low, moderate, and high. Again, the trapezoidal membership functions are defined for this one. Okay. Output. This may be in form of this may be from 0 to 30. Okay, and these 0 to 30 is also defined in terms of the linguistic one is low, medium, and high. And for all those three things, we have used the trapezoidal membership function. Okay, we are developing the Mamdani. Antecedent part of the fuzzy rule are combined using this AND operator. Means AND is denoting the minimum, OR is denoting the maximum. Implication is minimum, aggregation is the min, or defuzzification is centroid method. Okay, and we are using, this is basically the rule base. If soil moisture is dry and temperature is low, then irrigation is high. If soil moisture is dry and temperature is moderate, then high. Basically, you know, if you are using 3 fuzzy sets for this soil moisture, 3 fuzzy sets for temperature, and 3 fuzzy sets for the irrigation, you have 27 this kind of the rule, 3 into 3 into 3. All permutation and combinations you will have. But most of them are not of use because you have that kind of the information that only these 7 rules are going to be used in the range of this input. Now, this is the case. Suppose I have the sample A, sample A, whose soil moisture is 35%, temperature is 32%. I have to determine that what should be the irrigation for this one. There is sample B, that soil moisture is 15%, temperature is 28%, then what should be the irrigation for this one? Okay, I told you these are the rule base, 9 rule base. If soil moisture is dry and temperature is low, then irrigation is high. If soil moisture is dry and temperature is moderate, then irrigation is high. These 9 rules I have used as a rule base. Okay. Then I told you how the inferencing will be done. I will compute the membership grade of this 35 in fuzzy sets dry. This has come 20.25. I will compute the membership grade of this 32 in the fuzzy set low. It is not the member of this fuzzy sets. So the membership grade of temperature in this fuzzy set low is 0. How the firing strength will be decided? I told you these are connected with AND operator. So AND denotes the minimum. You will take the minimum of these two. That will be the firing strength. So firing strength of first rule is your 0, means it is not going to be fired. In the same way, firing strength of each rule is computed. Some of them are not going to be used because here you can see those firing strengths are having the 0, 0, 0, 0, 0, 0. So rule 1, rule 2, sorry, rule 3, rule 4, rule 6, rule 7, rule 8, and rule 9 are not going to be used. Only 2 rules are going to be used, that is rule 2 and rule 5, to find out the output when the input is soil moisture 35% and temperature is 30%. Now, I will see what is the consequent part of this rule 1. Consequent part of this rule 1 is high. So the fuzzy set high, sorry, this one, the fuzzy set high will be clipped by 0.25. Medium membership function clipped with the 0.5. High will be clipped with 0.25. You will have the combined surface. You will find out the center of gravity of that surface. That center of gravity will give you this 12.5. Okay, so it simply tells you that if the soil moisture is 35% and temperature is 32 degree, then the irrigation should be 12.5 millimeter per day. Okay, इसी तरीके से simple we have also computed that, you know, if the sample B whose soil moisture is 15%, means it is more dry than sample A. Temperature is moreover same. In this case, you will find some high amount of the irrigation is required per day. This is also computed using this one only. This I have taken a very simple example. Okay, like you have, because agriculture system is not so simple that you decide the things. You decide the thing taking only 2 inputs or 3 inputs. Okay, you will decide, you will have the number of inputs there. Okay, you will have the number of inputs, you will have some certain kind of the relationship in input as well. Okay, that is going to affect the output. So you have to also consider that part, but you can include more complexity in this inference system to have some rational result. Okay. Another thing, because I could not include, because of the time shortage, time was allowed only for 1 hour. I could not include the example of the fuzzy inference system for this Sojano fuzzy inference system. As I told you, we don't need the defuzzification for the, we don't need the defuzzification in, we don't need the defuzzification in Sojano fuzzy inference system. It's simply computed by the weighted average. Okay, but there are a lot of kind of the things, adaptability, robustness, sensitivity, that can be included very much in the Sojano inference system. Because most of the times you are interested to develop the fuzzy system in such a way that it adapts the things. It is robust, okay, and it is capable of adapt the small changes. Okay, so you should have that kind of the thing. So you can include, or you can integrate it. In fact, the things are going to be integrated in terms of learning kind of the things, deep learning of neural network. Okay, that has also been integrated with this fuzzy inference system to have the adaptive neuro fuzzy inference system, which thinks like the human. Okay, so they are very much adaptable in nature. They are very much robust in nature. Okay, so this I have included in my presentation, that a simple example. But of course, there are some limitations and challenges as well. The performance of the fuzzy inference system is defined that how accurately the fuzzy rules are defined. Okay, as you know, the rule base are working like the memory. Okay, so जितना ज्यादा मेमोरी आपके पास होगा, उतना ही आप ज्यादा अच्छे डिसीजन लेने के लिए कैपेबल होगे. It also applies on the fuzzy inference systems. Okay, and it is basically depending very much on the expert knowledge. Either the knowledge will come in from the expert or from the observations. And all these models are data-driven models. Okay, so in data-driven models, one thing is there, they are limited to that range only. For example, if I have taken the range for the input for soil moisture in 0 to 100 and temperature in the range of 10 to 45. So this model is bound to take the input in this range only. If it goes slightly outside this interval, they are not going to produce the rational result or good results. Okay, this is basically the limitation of each and every data-driven model, that they are bound to that one. Okay, so this is sometimes they are computationally intensive. Like the computational cost is also there. Like they are very much complex. As I told you, the accuracy of any fuzzy inference system depends upon the expert knowledge and data quality. In fact, Data quality can be compromised because I told you this fuzzy system goes very good in case of the imprecise information. Okay, and imprecise information always come from the observations. Okay, like you do some mistake. We are human. We are committed to do some mistakes. So we sometimes we don't have the precise information, precise data, precise knowledge. In that case, they are going to be very good in the natures. Okay, and ये अभी हो रहा है as today's nowadays it is the era of artificial intelligence. So lot of things of the artificial intelligence is depending upon this fuzzy inference systems. We are taking fuzzy inference system is combined or integrated or fused with the machine learning techniques and some other techniques to make some more intelligent descents to give a powerful tool to this artificial intelligence. So these are also being done. A lot of things has been done, now the data we have in field, we have the sensors, automatically the data is coming into the system. If you have developed some kind of the fuzzy inference system in your it is taking automatically data from the field as an input, then you have a wonderful tool in your hand. Okay, so these are the future prospects. You can integrate, even it is integrated with the machine learning techniques. Okay, but of course, artificial intelligence has no limitations. You can integrate your fuzzy inference system with this artificial intelligence. This is being used fuzzy information, fuzzy-based smart farming systems, real-time monitoring using Internet of Things and fuzzy logic. And I should include some example of the decision-making problem for this agriculture. You will find the very wonderful applications of this fuzzy set theory in this multi-criteria decision-making problems. If you are interested, really, if you want to explore, you go the multi-criteria decision-making problems using fuzzy systems in agriculture sciences. Okay, these are some conclusions which can be made by my presentation. Okay, so that is all from my side, and I think I'm very much on time, and I'm very sorry for the inconvenience caused because of some technical failure from my side.
Thank you so much, sir.
Yes.
Thank you so much, sir. You took time out of your busy schedule to deliver the talk on this FDP. That was quite an interesting topic. Fuzzy logic has application in many fields, like the agriculture is not an exception to that. Now the session is open for any kind of discussion and question. If anyone has any participant, please.
Good evening, sir. Sir, you discuss about different membership function while analyzing what is the criteria to choose among different membership function, and does choosing different membership function will have any effect on analysis? चले गए क्या?
Okay, so I think our speaker has already left. So thank you today for your participation. We'll continue tomorrow on the last day of the FDP. There is an announcement for the last day. Actually, there is a slight change in the schedule of the program tomorrow. The program of the last day will start at 2:30, and we'll have two speakers again tomorrow for session 1 and session 2, and then we'll have a little valedictory session for the FDP. So I repeat the same thing again. The program tomorrow will start at 2:30 p.m. Thank you for joining today. We'll continue tomorrow from here. Thank you, everyone. Just sir, आगे सर आगे सर ने एंटर कर दिया. नहीं कोई सर हैं सर. हाँ. Sir, are you here with us? Actually, you are on mute, sir. Can you unmute your mic?
Yeah.
Okay. Sir, thank you for taking time out of your busy schedule to deliver such an insightful lecture on such an interesting topic. Actually, one audience had one question, sir. Can he
Yeah.
go ahead with that?
Sir, I do have one question.
Yes, please go
Hello.
ahead.
I want to ask us, can you put some light on every uses of fuzzy logics in crop in prediction?
Can you speak a little bit loudly?
Sir, I want to ask uses of fuzzy logic in crop in prediction.
Sir, she's
Crop
asking
in
that
prediction.
what are the applications
Can
of
you put
fuzzy
some
logic in
light?
prediction?
Yeah.
किसमें सावन?
Fuzzy applications of fuzzy logic in predictions.
Yeah. Basically, there are in two way you can use this fuzzy set theory for the prediction or for the forecasting. Like, you know, you will find the number of applications or number of models that are fuzzy time series forecasting models. Okay. But for that one, you have to some kind of the knowledge of this partition product of the fuzzy sets, relations, and all those stuff. But you can also develop the fuzzy inference system for the prediction, for the forecasting. Basically, what you can do, suppose you have the observation for the year 2024, you have the some observation for 2023 or 2022. So what you can take, you can take the previous data other than 25 as the input variables. Okay, so you can take if you see, like, you know, the forecasting of the current year is depending upon the previous year only, one previous year only, then you can develop the fuzzy inference system using the last year observation only. If you feel there is a relationship between the output variable on the previous 2 years value, then you can take the two last year's observation as the input variable, and you can go with this fuzzy inference system. But for exact forecasting, I will suggest you that, you know, you apply the fuzzy time series forecasting models. Okay, so for that one, you should have a little bit idea about of this fuzzy time series. And nowadays, some in some GitHub or some Google library, you will have some built-in functions also there. There you can use the data and decide the model. Your forecasting will be done.
Sir, there is a followed question. Like, if this is the era of AI, so
Yeah.
using fuzzy and using AI, which one will be better off? Like, there is quantum also.
Yeah, you can say AI is a superset and fuzzy set is a subset. Okay, basically, AI is taking so many things. I know it is taking the deep learning techniques. It is taking the statistical techniques. It is taking the conventional techniques. It is taking the soft computing techniques. Okay, so all these are the parts of artificial intelligence. They contribute a significant amount in the field of artificial intelligence. Like, you know, nowadays everyone is talking about this. Basically, nowadays the things has been changed. If you see the encyclopedia of the encyclopedia of this intelligence, you will find, you know, what is the definition of intelligence? Definition of intelligence says that if a person does not repeat the same mistake, he or she is the intelligent. Okay, and
Yes.
when you are not supposed to repeat the mistakes, it means you have learned from your past mistake. हमें आगे गलती करेंगे, but गलती repeat नहीं होगी, mistake repeat नहीं होगी. You are free to do the new mistakes, but the old mistakes will not be repeated, because if old mistakes has been repeated, it means you have not learned from your past, from your mistakes. Okay, और ये जब हम ये काम करते हैं, it means we are strengthening our knowledge base. Okay, and knowledge base is the part of our fuzzy inference system or any knowledge-based system. Okay, so they all contribute the significant amount in the field of artificial intelligence. You cannot say that, you know, of course, if you are going in field of machine learning, if you are going in field of the fuzzy set theory, if you are going or in some or in other data sciences, you are the part of this artificial intelligence. You cannot say, you cannot be the one thing in artificial intelligence. All these are the modules developed for the artificial intelligence.
Okay, sir. Got it. Thank you so much for your.
Okay, thank you.
Any other questions from any other participant? Okay, I think that will be all, sir.
Okay.
Thank
I
you.
tried my best to avoid the hard and hardcore mathematics from the presentation, but you know, that is also the part of your focus should be there. Like, you know, basically the thing is that first the, you know, observations, you need the data. You need the data for this fuzzy inference system of for developing any system. The data will either come from the survey analysis or it will come from the mathematical model. Okay, so I'm not saying, like, you know, the fuzzy set theory, if you are going with the fuzzy set theory, then you don't need to study this mathematics or statistics. No, they have their own importance. Okay, one major difference, a lot of people get confused, like, you know, what is the difference between statistics, probabilistic uncertainty, and this one, where the probability is always lying between 0 and 1, and membership grade is also lying between 0 and 1. Okay, probability measure and fuzzy measure, they also coincide with each other at the higher level. But there is the big difference is that the probability theory tells you whether the event will happen or not. But fuzzy set theory tells you how the event will happen. Fuzzy set theory cannot tell you whether the event will happen or not. It can be determined only by using the probability theory. Okay, so you should means everything has its own importance, and I'm very happy that you choose a topic like, you know, the applications of mathematics in agriculture. Okay, so fuzzy set theory और ये सब चीजें तो बाद में आती हैं. You should promote, or you should you know, motivate your students to study the mathematics.
Yes, sir. So the people who are first time being introduced to fuzzy set, that was quite an insightful session, because you, as you told, that hardcore mathematics you do not involve, but the way you presented the applications in agriculture by the your analysis and your research paper, that was very helpful for the participants also.
Okay.
So thank you again, sir, on the behalf of organizing committee and all the participants. Again, I would like to thank you for accepting our invitation and delivering a talk on the question of this FDP. Thank you so much, sir.
Thank you. Okay. All the best.
Okay. Thank you, sir. This will be all for today. We'll continue tomorrow again at 2:30 p.m. So tomorrow will be the last day of the FDP. There will be 2 sessions again and the validatory session. Thank you, everyone. So this will be all for today.